My experiment is called Fallen Angel, which will make more sense in a second. This experiment compares the motion of a fallen object when drag force is included and then when it's negated. The purpose of this experiment, or the reason why we're interested in it to begin with, is to determine if drag force is a negligible interaction in a system. So, as you can see, drag force counteracts force gravity by having an opposite direction. Using computational modeling, we will compare the system on the left to the one on the right. I predict that when drag force is not considered in a system, the object will displace over a greater distance over an interval of time, meaning that objects without drag will move faster. In this experiment, the system is a pair of old costume wings, and the interacting surroundings are the earth and the air. Here's my video. You can see the wings falling. They start at the origin and then move in the negative y direction. The position over time graph resulting from the experiment is not linear, showing that the velocity is changing over the time period of 0.4 seconds. This can be attributed to Newton's second law, which states that objects that interact with the Earth's gravity, or g, a gravitational constant of 9.8 meters per second squared. But we should also consider the interaction drag plays on the system in order for our computational results to model real-world data. We can find drag force by squaring an object's velocity and multiplying that by a drag force coefficient, notated b. The drag force coefficient had to be predicted for this experiment because it's different for every single object. The greater this coefficient, the greater the drag force. For this experiment, I determined that b equals 0.3 because that best reflected the experimental results. In my prediction, I thought that no drag force would yield a faster pair of wings, or wings that displaced over a greater distance in a certain period of time. In this graph, however, you can see that the tracker data, or the experimental data, actually displaced fastest most of the time, but ended up being outshone by the predicted data that didn't include a drag force. So in a way, I was right, but that's still interesting to see. So really, what does all this information mean? Without drag force, the velocity keeps increasing over time. Note how the magnitude increases down the y-axis, so even though it looks like it's decreasing, it's really increasing. Terminal velocity occurs when there's a point that the velocity is no longer increasing, and that happens when there is a drag force. So why does terminal velocity occur when there is a drag force? Because drag force counteracts the gravitational acceleration, acting as an opposing force that reduces the gravitational force's influence over time. So what if the angel didn't fall from heaven, but was thrown? AKA, the wings didn't fall from my balcony at a resting velocity, but were thrown. So if the wings were thrown, the magnitude of the velocity would be greater, but we would still have a terminal velocity, meaning that the velocity would still be at some point not increasing anymore. However, because the magnitude is greater, there's still a chance you can crush your angel.